All right, so today it appears to be a thinly attended class. Is it because of the assignment? Or is it because of general fatigue? All right, so what we will discuss today is, yes, so in the last class, what I showed you is that there is a second energy scale that we have so far not considered and that we are going to consider now. The second energy scale is related to the stiffness of the phase, and that is what is called as the superfluid stiffness. This is an energy scale in addition to the superconducting energy gap that we need to consider if we have to consider all the excitations that can influence the superconducting state. Okay, so having set up the energy scale J, now let's try to see, at least phenomenologically within a toy model, what does phase fluctuation do? So we'll look at the manifestation of phase fluctuation. So by the way, did you guys calculate J for clean superconductors, which I have told you in the last class? Who has done it and how much did you get? Let's say in terms of Kelvin, in units of Kelvin. Okay, none of you calculated it. I think you ought to calculate if you have to appreciate this. All right. Now, the general derivation of phase fluctuation in a superconductor, it's reasonably intricate, and you start with an action and then you calculate the phase fluctuation. So it's rather involved field theory. What we will do instead is, for the purpose of this course, we will take first a toy model. And in fact, the good thing about this toy model is that whatever expressions you derive from this toy model, modulo some factors of the order of unity, is exactly identical to what you would get from a much more complicated complete calculation. So in this toy model, we will assume two small superconducting islands connected by a weak link, and this weak link has all dimensions of the order of xi. Now, the only thing that we will assume now is that this object is small. Now, what do I mean by small? What I mean is that it has small enough capacitance such that the Coulomb energy cost Q square by 2C, the Coulomb energy cost of, let's say, adding one electron here. Adding one electron means Q has to be equal to E. So, let's say E square by 2C is not negligible. Is not negligible compared to the Josephson energy scale EJ. Okay, so this is the model that I will start with. Now this is a model, of course, this kind of picture we have drawn a lot, so we are familiar. I know that here the current through the weak link will be given by IC sine theta. This is the Josephson relation that I have calculated before, that I have derived before, I'm sorry. And IC is twice EH cross into superfluid density. Now here I will put N as 0 because we will see later on the effect of phase fluctuation is to reduce the superfluid density. So when I am putting N as 0 here, this 0 refers to the superfluid density without phase fluctuations. So when phase fluctuations are incorporated, then I will have this Ns which will become smaller than Ns0. And then here I have area by length, and since I have taken all these dimensions to be of the order of xi, so this becomes xi. So this is what I know from the classical Josephson junction that I have calculated. Now when I am talking of classical Josephson junction, this is an oxymoron. Josephson effect is a quantum mechanical effect, but what I mean by classical is that I am not considering any fluctuation effect. So it's not there is, in the true sense, if you start from classical mechanics, there is no Josephson effect. Okay, now the point is that theta here we have assumed to be well defined. So theta is just dependent on the supercurrent that is passing through the link and the critical current of the junction. However, in principle what happens, theta can fluctuate. Theta can fluctuate about a mean value. Now, you already know that theta can fluctuate when we did the phase slips in nanovats. However, there the fluctuation was actually large fluctuation. It was just rotating by 2 pi. which is actually a huge fluctuation. But instead of doing this large fluctuation, it could also have small fluctuations about its mean. Fluctuations that in amplitude are much less than 2 pi, much less than pi, but nevertheless this theta is not a constant, it's fluctuating about its mean value. Now why would it fluctuate? As it so happens, and this is what we will be deriving now, there are two origins for that. The first origin is of course thermal. So you have thermal phase fluctuation, and the second effect is that, and this is more complicated, this quantum phase fluctuation. So we will start with the thermal phase fluctuation. But before that, before we start with any of this, let us see what is the effect of if the phase is fluctuating. If the phase is fluctuating, what does it physically do? Okay, I think I have to switch off this. Again, this is misbehaving. Sorry. And restart the OneNote. Good. All right. So let me assume first that this theta is not a constant, but rather it has a mean value plus a time dependent fluctuation about its mean value. The first observable effect that I will have is on the supercurrent because that depends on theta. So the supercurrent IS now will be IC into, so this is the average supercurrent. I want just the DC value, so I am integrating over characteristic time that is much larger than the fluctuating time scale, and sine theta plus delta theta average. Now you know that this will be sine theta cos delta theta and cos theta sine delta theta, but average of sine delta theta, if theta is fluctuating between about 0, so if delta theta is a fluctuation about 0, then that would average to 0. So therefore what I will have here is IC average of cos delta theta into sine theta. The other term becomes 0 because sine delta theta average is 0. Now, if of course, this is only valid if my delta theta is small. So therefore, I will make straight away the assumption that delta theta is small, and I will write 1 minus delta theta squared by 2, average of that. So that's the root mean square fluctuation in theta by 2 into sine theta. All right. So this immediately tells you that the net result is that you have a new critical current which is lower than the earlier critical current. This is what I would call IC prime, and IC prime is now smaller than IC. So the effect, the first direct effect of this fluctuation is to suppress the critical current. Now, of course, you know that the critical current is related to the superfluid density, and therefore this equivalently means that the superfluid density in the weak link has got suppressed not on the pads but on the weak links, not on the islands. And this will be given by exactly the same expression. Okay, now of course, when we are considering a weak link, the superfluid density is not very important here because critical current is what I will be measuring for a weak link. And measuring directly the superfluid density is difficult because I have to measure the penetration depth. Now on a weak link which is so small, how do I measure the penetration depth? Nevertheless, the reason that we are still writing this expression is because eventually we will not restrict ourselves to weak links. We will want to understand the phase fluctuation in bulk samples when the superfluid stiffness is small, and in bulk sample measuring the critical current is much more difficult. Measuring the penetration depth is the natural thing to do. So whether you work in terms of the critical current or the penetration depth, which gives you NS, is entirely an experimental consideration of what is the size and shape of your sample. So this is more relevant for two D and 3D samples. All right. Okay, good. So this is what happens when I have phase fluctuation. But then how do I calculate how much this phase will fluctuate? So how do I calculate, in other words, delta theta square? Okay, now delta, as I told you, there are two origins of this fluctuation. One of the origin of this fluctuation is thermal phase fluctuation. The second origin of phase fluctuation is quantum. So we will take them separate. First, let us take thermal phase fluctuations. So for this, I have to start. So I know that thermal phase fluctuation will cause essentially an energy fluctuation of the order of kT. Okay. But the question is, I have to know which energy scale I will equate to kT. So for that, first let's calculate what is the energy stored in a Josephson junction in the weak link. This will be given by Is into V dt. So now V dt, I can use the Josephson relation, and I will get H cross by 2E into d theta. Now Is is IC sine theta. So therefore I can write as IC H cross by 2E sine theta d theta. This quantity is the Josephson energy, and this is Ej. I have already invoked Ej once right at the beginning here, and this Ej is that same Ej that now you have a complete expression for. So this will be some constant minus Ej cos theta. Of course, my lowest energy state is when theta is 0, so therefore it has to be cos. It has to have a minus sign. Okay. So now, what would happen in the presence of phase fluctuation? In the presence of phase fluctuation, Ej will get modified. Why and how? You can see Ej is directly related to IC. IC has gotten modified to IC prime, which is IC into 1 minus delta theta square average by 2. So therefore, Ej will get modified to Ej prime, and that will be Ej into 1 minus this. So now therefore the change in energy delta Ej because of the phase fluctuation is Ej minus Ej prime Oops, sorry, this should be cos theta. It's a cos theta here. Alright, now let me assume that there is no current in the junction. So if there is no current in the way passing through the weak link, then of course theta is 0. So this cos theta is 1. So now I can equate this delta Ej for theta equal to 0, which is nothing but this quantity, and this will be of the order of kT. Okay. So now, okay. So delta theta squared by 2 is kT by Ej, and therefore IC prime by IC, which is equal to Ns by Ns0, that is this. Now remember that this expression is only valid when delta theta is small. So therefore delta theta small corresponds to the harmonic approximation. When delta theta becomes large, you will have anharmonic terms that will become important. So this is valid only at low t. Okay. Now, what does this mean? This means that, remember that now when I am doing this phase fluctuation, I am pretending that quasi-particles don't exist at all. So I am considering only the phase degree of freedom, and on the other hand completely ignoring the quasi-particle degree of freedom, the fact that the pairs, some of them will get depaired, I will have excitations. I will have quasi-particle excitations. But if I had only phase fluctuation, then my superfluid density would vary linearly. So of course it would vary linearly at low temperature. At some point there will be anharmonic terms that will get important. I don't know exactly where that will happen, but definitely close to Tc. So at some point the anharmonic terms will cause a rapid suppression, and the superfluid density will crash. So this axis is temperature. Okay. However, at low temperature, thermal phase fluctuation tells me that this slope should be linear, negative linear. Okay. This is the hallmark of thermal phase fluctuation. Now let me go back to this expression here. And in this expression here, let's look a little bit at the expression of Ej, because we need to understand what this expression of Ej is. As I told you, this toy model is for us just an instrument to understand the bulk, let's say, bulk superconductor like film or crystals. So let us understand what this Ej is. So this Ej is, what is the expression? H cross IC by 2E. Now that is, if I put the expression for IC, then I will get twice H cross square NS0 Is this expression familiar? Does this expression remind you of something? Modulo the factor 2 and so on. Actually, I have this 2 also will go. Because I have a 2 here. The expression for IC, just to refresh your memory, is twice C H cross NS0 divided by M into xi. So plug this in here, the 2 will go, the E will go, and this is what you will get. Okay, good. So this expression, what does it remind you of? Does it not remind you of anything? What was the expression of J that we derived in the last class?
Sir, it was H cross square NS xi and divided by 8m.
Other than the 8, it's identical. Okay? This is the expression that we had derived in the last class. For 3D it is xi, for 2D you had a thickness that comes here. But look at this expression. And look at today's expression. It is exactly the same. So J that we had derived in the last class was except for a factor of 8. This is the same expression. So J in a bulk superconductor, in a 3D superconductor, the role played by J is the same role as the one played by EJ here. So in fact, Ej is the same as J for one dimension. Now, this is what will happen for thermal phase fluctuation. We have derived this only for a link. I will show you later on, I will argue later on how we can extend this for a sample. But let me show you some situation where one actually gets this linear dependence experimentally. Okay, just hold on a minute so that I can open this file. Okay, good. All right, so you know that if you put in disorder in a superconductor, then the superfluid density comes down. The superfluid density decreases. And then at strong disorder, at some point, J, the superfluid stiffness, can become small enough that it becomes smaller than the gap. So these are a set of samples which are very disordered, where the superfluid stiffness has been brought down to a level, to a value that is smaller than the superconducting energy gap. So phase fluctuations dominates the superconductivity here. Okay. What I want you to see is this data, for example. So these are set of sample superconductors which are increasingly more and more disordered, but here the ones that you see, they follow very well the BCS behavior. But when you go more disordered than these, which are here, then they start deviating from the BCS behavior. And let's take this most disordered sample, which is here, and you see that at intermediate temperature, you have a large range where the superfluid density is varying linearly with temperature. Is it clear? Is there any question? Okay. So if at high temperature, of course, as I told you, you will have anharmonic terms that will become important. That is horrendously difficult to calculate. So, but when you have nonlinear terms that dominate, the superfluid density precipitously drops and will go to zero. Fine. But the immediate question is, what is happening at low temperature? What I derived, if it is correct, then this should have been linear all the way up to t equal to 0. So it's this red line, which is the linear feed, should have extended, and at 0 my superfluid density should have gone here, out of the scale possibly. But instead there seems to be something that is limiting the superfluid density at a much smaller value. So if I want to draw a cartoon now of this, then what is happening is this. That instead of the superfluid density increasing linearly up to t equal to 0, it appears to be getting cut off at some value here. So now the superfluid density appears to be something like very slowly varying or a constant at low temperature. Let me draw this a little differently. And then I have a linear behavior and then some kind of a drop. That is an harmony. So this linear part I understand from thermal phase fluctuation, but what is this? To understand why at low temperature I see this kind of flattening, I have to now consider the second kind of phase fluctuation that I have been talking about, which is quantum phase fluctuation. Now, quantum phase fluctuation, before we do any mathematics, let us try to understand this a little bit physically. So, I have these two islands here. Connected by this weak link. So far, we have only considered one energy scale, that is J, Ej. But you see, if there has to be phase coherence that is established, then it is absolutely important that there are some exchange of Cooper pair from one side to the other. If there is no exchange of charge particle from one side to the other, in particular, if there is no exchange of Cooper pair from one to the other, then it is as good as two isolated superconductor. And for two isolated superconductors, there is no reason that their phase would be the same. So therefore, in that case, the two phases would be completely indeterminate. Now, the problem is, since these are small islands to start with, the moment I have one exchange of Cooper pair, I increase here. Suppose I had n Cooper pair here and n Cooper pair here. So I exchange here, I get n plus 2 charge here. I will have a charge of n plus 2e here, and here I will have a n minus 2e of net electronic charge. Of course, that means that the net charge on this island will become 2e and the net charge on this island will become minus 2e. The rest is compensated by the positive ions. Now, that immediately means that there is an energy cost. And what is the energy cost? That energy cost is the Coulomb energy cost. So the Coulomb energy cost is, if let me denote this by Q, will be Q squared by 2C for both these q square by 2c for this island and q square by 2c for this island. So therefore, the total energy cost is q square by c. So you have this energy cost of transferring a particle. So now, if suppose your energy cost of transferring a particle is very large, you have taken very small grain, q square by c is very, very large, then there will be no exchange of particles. And if there is no exchange of particles, so there will be no charge going from one side to the other because the Coulomb energy cost would be too much. And in that case, the phase will be completely indeterminate. On the other hand, if the Coulomb energy cost is very low, if your islands are very large, in that case, the exchange of particle will happen much more efficiently. And when the exchange of particle happens much more efficiently, the phase will get steeper. So the phase fluctuation will reduce. This concept is what is embedded in superconductivity. Actually, it's a quantum mechanical concept of coherent state, which is called the number phase uncertainty principle. The number phase uncertainty principle tells you that delta n, delta theta is greater than almost equal to 1. Delta n is the number fluctuation of particles in the two islands. In other words, delta n is the number of charge that is passing through the weak link, and delta theta is the fluctuation in the phase. Okay? So this is an effect that does not depend on temperature. It depends on two energy scale. The first energy scale is EJ and the second energy scale is EC. It's a competition between this Josephson energy scale and this Coulomb energy scale. And if the Coulomb energy scale wins, then you will have a large delta theta, which means that you will have a large phase fluctuation even at t equal to 0. This is the reason why instead of the superfluid density, which should have gone all the way up to here, has come down here. This is the effect of quantum phase fluctuations. And since it is temperature independent, till thermal fluctuations take over, you have essentially a temperature independent superfluid density. Okay, now we can do a little bit better than this. And to do a little better than this, the first thing that you have to prove is that number and phase are conjugate variables. That is why you have this uncertainty relation. So this is something that so there are many ways to do it. There are many very rigorous ways to do it. And there are some slightly less rigorous but more intuitive way to do it. This is something that I will be giving you today as an assignment problem. So it's very simple. Let me explain the problem, and working it out will not be difficult. So we start from the VCS mean field Hamiltonian. By now you know the VCS mean field Hamiltonian. Let's write the general Hamiltonian. It really doesn't matter. Yeah. Okay. This is the VCS mean field Hamiltonian. Now you know that delta K is this quantity over here, and you also know that in its most general form, the VCS wave function is given by this. Okay, so now this phase factor e to the power I pi k, you incorporate it in the C case. So in other words, you assume that your C case are replaced by these objects which have the phase, because the phase is actually the phase of the electrons. So therefore, delta K will become delta K modulus e to the power I phi k. Now what you have to show is very simple. You calculate dnk of dt, and how will you calculate dnk of dt? So nk of is of course how will you calculate this? You will calculate using the Heisenberg equation of motion. And then you also calculate this derivative. So calculate these two quantities, see what you get, and from that deduce what's the relation between number and phase. With that input, in the next class on Friday, we will continue with quantum phase fluctuation. So you are supposed to submit your assignment today. The next assignment you can submit it later on. I will give a reasonable time frame. But this particular problem, get it done before Friday. It's an easy problem, but because in the next class we will be actually using the number phase uncertainty principle to calculate quantum phase fluctuations. All right, I stop here. Questions? Okay, so that is remarkable. There are no questions, which I believe that all of you have followed this class in its completeness. And we'll meet again on Friday.